This is Biot-Savart law. Let me write it in black color pen. Biot-Savart law, according to which there's a wire in which there's a current, and at any point P, the magnetic field at any point, keep your right hand thumb rule pointing to this direction, and the curled finger, obviously at this point the magnetic field will be inward. The curled finger is going inside at this point. That shows the magnetic field is inward. Inward magnetic field can be represented like this with a cross mark, or you can also write it as negative z axis or negative k. In vector it's minus k. So there's a magnetic field dB at any point P which is at a position vector r from a current element dl, which is a part of the length of the wire L, which is at a perpendicular distance A, in such a way that this angle is theta, this angle is 90 degree. This is something you need to understand. According to Biot-Savart law, dB is proportional to I dl sine theta by r square, and dB is equal to proportionality constant mu naught by 4 pi I dl sine theta by r square. In electric current it was 1 by 4 pi epsilon naught. Here it's mu naught by 4 pi. Mu naught is nothing but permeability. The permeability is 4 pi into 10 to the power minus 7. The SI unit of dB itself is Tesla. Therefore, Tesla meter per ampere. You can imagine it's meter square and there's meter and dl, and they'll get cancelled. So mu naught is 4 pi into 10 to the power minus 7. And substitute that value here. The 4 pi get cancelled and will become 10 to the power minus 7. Okay, supposing you want this is Tesla. This is Tesla, the unit. So then what is it? You have a straight wire carrying a current I. You want to find the magnetic field at any point P, which is at a position vector r from a small current element dl, which is a part of the length of the wire L, where A is the perpendicular distance and this being theta. The magnetic field will be pointed outwards because the current is flowing in this direction. You keep a thumb pointing in the direction of the current. The curled finger which go inside at this point, which shows the magnetic field is inward, and that magnetic field is proportional to I dl sine theta by r square, where I is the current flowing through the wire, dl is the current element here, and sine theta is the sine of the angle between the current element and the direction which I'm measuring the magnetic field, this direction which I'm measuring the magnetic field, and inversely proportional to square of the distance between them, where dB is equal to mu naught by 4 pi into I dl sine theta by r square, where mu naught itself is known as permeability, which is 4 pi into 10 to the power minus 7 Tesla meter per ampere. And this can be represented in vector form. If you multiply and divide by an r vector, I dl sine theta r vector by r cube, when you do that, the sine theta is there. It has to be a cross product of dl and r whenever there's a sine theta, and therefore dB vector is mu naught by 4 pi into I dl cross r vector, and dl cross r vector by r cube, where sine theta is already hidden. So this is the way you represent in vector form, and it's an SI unit is Tesla. So here comes the first application of Biot-Savart law. The first application of Biot-Savart law is take the same conducting wire. It is going to be useful in finding the magnetic field at any point due to infinitely long wire. This is supposed to be an infinitely long wire. I'm trying to find a magnetic field at any point P, which is again a distance of r, position vector r. Because of the small current element dl, I'll experience a magnetic field dB, which is inside the paper, which is minus k direction, obviously, and you have a perpendicular distance A. This is theta, and this is 90. Let's call this as phi. Supposing it's an infinitely long wire, very long wire, imagine my head is here. I'm going to lift my head up to see the tip of the wire, making an angle phi 2. Bending my head to see this tip, which is minus phi 1. These are the angles on the top and the bottom, and you just have to imagine yourself looking up and down. Now you write Biot-Savart law, dB is equal to mu naught by 4 pi into I dl sine theta by r square. You take this right triangle, the theta plus phi plus 90 is equal to 180. Therefore, theta plus phi is equal to 90. Therefore, theta is equal to 90 minus phi. When you substitute that here, the sine theta will become a cos phi. Sin 90 minus phi will become cos phi. So, one is sorted. Next, dl. You want to find what is dl in the formula here. So, you take this right triangle again. You write, this is L. Okay, therefore, tan phi is equal to L by A. So, L is equal to A tan phi. So, dl itself is A into secant square phi d phi. When you differentiate this, you get this. So you found DL. Let's find R square. From this again right angle triangle, you know R square, which is the hypotenuse here, which will be equal to A square plus L square. And you know L itself is A tan theta. So A square plus A square tan square phi, sorry, which will be A square common into secant square phi. Therefore, you know what is R square. Substituting all those values and plugging in here, mu naught by 4 pi into I into dl itself is A into secant square phi into d phi. A sin theta itself is, as you know, is a cos phi. By R square itself is A square secant square phi. Secant square phi get cancelled. A and the power A get cancelled. So then its integration of 1 dB is equal to okay, we'll keep the integration separately. We'll take out the constant mu naught by 4 pi I by A into integration of cos phi d phi, integrated from minus phi 1 to phi 2. The angle below and up is minus phi 1 phi 2. So integration of cos phi is sin phi, integrated from minus phi 1 to phi 2. When you put upper limit minus lower limit, you get sin phi 2 minus sin of minus phi 1. The sin of minus theta is minus sin theta, so sin phi 2 plus sin phi 1. Okay, and a mu naught by 4 pi into I by A will be there. Since it's an infinitely long wave which extends up to sky and extends up to the ground, and you're keeping your head here and looking up and down, you can say how much you would lift your head will be 90 degree up and 90 degree down if it's infinitely long wave. Imagine this situation. In that case, it's sin 90 plus sin 90, which will be 1 plus 1 2. Therefore, mu naught by 4 pi into 2I by A is a magnetic field B due to an infinitely long wire. Thus, you get, by using Biot-Savart law, you are able to get the magnetic field due to infinitely long wire. This derivation has never come for exams, but what if it comes, you better learn. But having said that, a you get a formula you get to know how to find a magnetic field at any point P due to infinitely long wire is mu naught by 4 pi into 2I by A. Supposing it's a semi-infinite wire, let me draw this horizontally. I'm placing my head here. Okay, which means I'm not even moving that side, rotating my head that side. Theta is equal to 0. One of the theta, only 190 degrees there. In that case, the magnetic field will be mu naught by 4 pi into I by A, because one of the sin 90s, sin theta will become 0, sin 0. Only another sin 90, sin phi 2 will become sin 90, and therefore that's mu naught by 4 pi into I by A. So if you consider a square, a wire which is a part of a square, just this part of the wire, we're going to consider the current is flowing anti-clockwise here. Keep your head here. You're going to look at this end and this end. You know, central angle is 90 degree. Therefore, the half of it is 45 and a 45. The way you're lifting your head is sin 45 plus sin 45. In the same formula, if you plug in sin 45 plus sin 45, it's 1 by root 2 plus 1 by root 2, which is 2 by root 2. So, root 2 I by A. So, the formula B is equal to mu naught by 4 pi into root 2 I by A. Okay, where A is the perpendicular distance, yeah? Which will be, if you know the length of the square, it is L by 2, where A is equal to length of the square by 2. So that will be the perpendicular distance. So what happens if they ask you for all the different sides, such as this, the current is going like this, you keep your thumb in the direction of the current, you see the curled finger will be like this, which is going to come out like this in this direction. If you consider it, will go and circle it around and come out like this. There will be outward magnetic field. Here also outward. Keep your thumb and see every side the magnetic field is going to be outward. So if you're going to consider all the sides, then the magnetic will be 4 into mu naught by 4 pi into root 2 I by A, because all the magnetic field, this will get 4 times because everything is outward, the vector is facing outward, so it has to be added. Supposing you're talking about a wire which is a part of a equilateral triangle here. I'm going to keep my head here and look at this end and this end. It's 120, so 60 and 60, which makes it phi 1 and phi 2 to be 60 and 60. Substituting in this formula, mu naught by 4 pi into I by A into sin 60 plus sin 60 is root 3 by 2 plus root 3 by 2, which is 2 root 3 by 2. 2 get cancelled, you get a root 3. So mu naught by 4 pi into root 3 I by A. Thus the magnetic field due to one wire is mu naught by 4 pi into root 3 I by A. And due to all these wires, supposing you're going to consider all the 3 wires, it's going to be 3 times, because you keep your thumb pointing to the direction of the current. The curled finger indicates that at this point, okay, the nails are going to be pointing outward. If you keep your finger like this, your nails are going to be pointing outside, which shows that from in the center, the magnetic field would have come out. From all the three sides, it's going to work like that. So then, therefore, it's going to be 3 times mu naught by 4 pi into root 3 I by a, adding all the vectors if you're considering all the three sides. So this is the application of Biot-Savart law, wherein you are able to find the magnetic field due to infinitely long wire, semi-infinite wire, a wire which is part of a square, a wire which is part of a triangle. But in this, what is A in a triangle? This is the perpendicular distance A. If they give you side of the square to be L, A is equal to L by 2 root 3. Because you take this triangle, this side is L by 2. You take this triangle and you want to find adjacent side. Tan 60 is equal to adjacent by L by 2, where A is the adjacent side, right? So then it's root 3 is equal to L by 2. So you want to find L, A, which is root 3 L by 2. Okay, cross multiply. Tan 60 is root 3. Root 3 is equal to A by L by 2. So root 3 into L by 2 is equal to A. So thus A is root 3 L by 2. Adi, you said it's L by 2 root 3. No, it's root 3 L by 2. So A itself is not L by 2 root 3. From this triangle, you know that tan 60 is equal to, tan 60 is equal to opposite is L by 2, adjacent is A. Root 3 is equal to L by 2A. So A is equal to L by 2 root 3. Yes, Adi, what you said is right. Therefore, A in this case is side of this triangle by 2 root 3. You should remember that. That's the value you should substitute. It's correct only. So next is the second application of Biot-Savart law, where you have a circular coil. You're trying to find a magnetic field at any point P, which is at a distance of r. The radius of this sphere is A. The small element dl, current element, the current is flowing in anti-clockwise direction, is going to exert a magnetic field dB in this direction. You will break it down into components, and this is dB sine theta, not cos theta. Why? Because in electric field lesson you put it as cos theta. The electric field and magnetic field are perpendicular to each other, so this will become dB sine theta and this will become dB cos theta. And considering another element diametrically opposite, you will get another dB, and so then this will become a dB cos theta. Here the dB cos theta component is getting cancelled, and you have to integrate dB sin theta over the entire pi meter 2 pi a, and for which you have to take, this is very critical, you take a circular wire and you're trying to take a point P. The P was outside, right, in the first case. Now you're considering the P to be at the along the radius at a distance of r. The radius itself is A. Considering a current element dl, current is flowing with dl. The dl and r are 90 degree. Therefore, applying Biot-Savart law here is mu naught by 4 pi into I dl sine 90 by r square. So this will be your dB considering this diagram. Due to this small current element, that's a dB. So then let's write that in place of dB, mu naught by 4 pi into I dl by r square. And what is sine theta? This is theta, and therefore the sine theta itself is opposite by root of r square plus a square. So it's a by root of r square plus a square. What you do is you can simply add an a square in this. It is not going to make a big difference, so that you will prefer to get it as r square plus a square whole to the power 3 by 2. Anyway, r is much larger than a. So r square plus a square into a by root of r square plus a square. When you write that, you get mu naught by 4 pi into I a by r square plus a square whole to the power 3 by 2 into integration of 1 dl. Integrate from 0 to 2 pi a. So 2 pi a. So mu naught by 4 pi into I a by r square plus a square whole to the power 3 by 2 into integration of 1 dl is L. Upper limit is 2 pi a. The 2 pi and a 4 pi get cancelled. So mu naught by 2 into I a square by r square plus a square whole to the power 3 by 2. So mu naught by 2 into I a square by r square plus a square whole to the power 3 by 2 is the formula to find the magnetic field at any point due to circular coil. Very important derivation. Please rewind it, play it again and again. Make sure you're clear with this, okay? So this is about it. And next is supposing at the center of the circular coil, at the center of the coil, you know r is equal to 0. The position vector r will be 0 if it's going to be at the center. So if you substitute that, r is 0, you will get mu naught by 2 into I a square by a square whole to the power 3 by 2. 2 and 2 get cancelled, a square and a cube get cancelled. Mu naught by 2 into I by a is the formula to find the magnetic field at the center of the circular coil. Okay. So you imagine if if current is flowing like this anti-clockwise, keep your curl the fingers. Okay, normally you point the thumb in the direction of the current, but in the case of circular coil, curl the fingers in the direction of the current. If you do that, you see the thumb will be outward. Therefore, at the center, the magnetic field will be outward. If supposing the current is flowing clockwise like this, keep your curled finger. Okay, curled finger, all the fingers in the direction of the current. And you see the thumb will be going inside the paper, so the magnetic field will be inward. So we can change around the curled finger and the thumb when it comes to circular coils. Okay, so that's you get a magnetic field B. And due to center of the circular coil is mu naught by 2 into I by A. Okay, next thing is Ampere's circuital law. Ampere's circuital law. Its integration of B dot dl is equal to mu naught into I. Just like in Gaussians, integration of E dot ds is equal to Q by epsilon naught. The E becomes a B. The ds is not, the current will flow through only a wire, so it can't be ds, it will be dl. And instead of permittivity, it will be permeability times the current. Okay, mu naught into I. This is the definition for Ampere's circuital law. The line integral of magnetic field over a closed loop is equal to permeability times the absolute permeability times the current flowing through the wire. The line integral of magnetic field over a closed loop is permeability times the current flowing through the wire. So define it. Now it's the application of Ampere's circuital law. The first application of Ampere's circuital law. What is the first application of Ampere's circuital law? First application of Ampere's circuital law is consider a solenoid. Pass a current I. The speciality about solenoid is it's got total turns N and then the total current is Ni at any instant. Okay, now consider a closed loop A, B, C, D. Okay, you're going to find, the solenoid itself behaves like a bar magnet where the field lines will go from north to south, and within the bar magnet it will be like this, correct? So then therefore, the magnetic field line is going to be like this. And AB, okay, let's write Ampere's circuital law, integration of A to B, B dot dl, which is B ds cos 0. Why? Because the angle between the magnetic field and AB is parallel to each other for AB. For integration of B dot dl for B to C. BC is like this, where the magnetic field is perpendicular, blue color. Can you see cos 90? So therefore it will be 0. Plus integration of C to D, B dot dl, plus integration of D to A, B dot dl is equal to mu naught into capital N into I, because that's what I is not anymore I, it's Ni. This will also become 0 because it's cos 90 for AD, because the angle between the AD and magnetic field is 90. So this becomes a 0, this becomes a 0, this will also become a 0. The reason being, a bar magnet, there will be no attractive force above and below and all. So this is above, the CD is above. So then therefore the magnetic field is 0 above and below. The field density is very less. Take a bar magnet, goes from north to south, in the distance far away from each other. Shows the field density is very less, so magnetic field is negligible and so 0. Therefore you only have one component, which is B dot dl from A to B is equal to mu naught into capital N into I. In B can be taken out, integration of 1 dl is mu naught into capital N into I. B into L is equal to mu naught into capital N into I. Therefore B itself is mu naught into capital N by L into I. And total number of turns by total length is equal to small n, which is the number of turns per unit length. Therefore B is equal to mu naught into small n into I will be the magnetic field due to a solenoid. This derivation is the first application. Next is a toroid. You know how a toroid looks like. It will be closely wound, slinky like this. Okay, imagine it's got a radius, R1 is the inner radius and R2 is the outer radius. The average radius will be A, which is R1 plus R2 by 2. And the current is going to flow through here within the coil, and so within the core of the coil is where the magnetic field is going to exist. Therefore the magnetic field inside is 0, the magnetic field outside is also 0. only within the core of the current carrying coil will the magnetic field exist. So now write by Ampere's circular law, which is integration of B dot dl is equal to mu naught into capital N into I, where when you integrate, B can be taken out common, integration of 1 dl integrate from 0 to 2 pi a is equal to mu naught by mu naught into N into I. So B is equal to mu naught into capital N by 2 pi a into I, and N by 2 pi a is nothing but small n. This is in the case of a toroid. So B is equal to mu naught into small n into I. Either way, the formula for magnetic field due to a solenoid or toroid is always mu naught into small n into I. The only variation being small n is equal to capital N by 2 pi a for a toroid and is capital N by L for a solenoid. And this is the first part of the lesson. Okay.